Hello, how's it going? In this video, we're going to be looking at number systems, specifically integers in binary, and some various signed and unsigned systems. So traditionally, numbers are represented in a decimal system. Let's say, for instance, 684. Now we can write it as 684, or we can decompose it in terms of its digits. So we can have 680 and 4. These positions are independent of each other. We could also sort of take this as a ones digit, which is 10 to the power of 0, a tens digit, which is 10 to the power of 1, and a hundreds digit, which is 10 to the power of 2. 680 and 4. Now, binary is pretty similar, but it's all based around 2 rather than 10. On and off, 1 and 0. So typically in binary, if we go through the powers of 2, 2 to the power of 0 is 1, 2, 4, just keep doubling. If, for instance, we were dealing with 8 bits, which isn't actually that much. Okay, let's represent some numbers here. So if I want the number 87, just off the top of my head, the way I would write this number in binary is I would sort of run from left to right, and I would say, well, do we have 128? No, we do not. Do we have 64? Yes, we do. And then, just for my purposes, I go, okay, 87 minus 64 is 23. So then I look at 23 and I say, well, does 23 have 32? No, it does not. Does it have 16? Yes, it does. And then again, for my purposes, I go 23 minus 16 is 7. And luckily I can see that 7 is 4, 2, and 1 with no 8. Now, of course, just for fun, we can recompute this. Yeah, 64 plus 16 is 80, and then 7. So far so good. Given any number, we can represent it. Let me go, I'll say 87 is in binary, so 0b for binary system. I hope I transcribed that correctly. Now, additionally, we can write this in octal. Okay, so we have O for octal. The octal system is based around powers of 8. So if I were to look at this, I'd have 8 to the 0 is 1, 8 to the 1, 8 squared, 64, and I probably don't need more than that, but I'll go times 8 again. On the other hand, I'm sort of showing the limitations of my capabilities here. 64 times 8 is 512, not 256. Okay, so we'll go through the same process. So we'll say, yeah, it's getting a little trickier, but we say how many 64s go into 87? 1. No more than that. If I have 2 64s going into 87, that's 128. That's too big. So again, we take off 64. That leaves us with 23. I say how many 8s go into 23? Ooh, not 3, because that would be 24, but 2. Okay. And then 23 minus 16 is 7. So how many 1s go in there? It's 127. 127. But remember, this is 127 in octal. So, in other words, I'm saying 7 times 1 plus 2 times 8, that's 23 so far, plus 1 times 64 makes 87. And there is in fact an easier way to compute this, and that is if we were to group bundles of 3 and then transcribe that into decimal. So this bundle of 3 has a value of 7. This bundle of 3 has a value of 2, if we're just reading that as pure binary, unsigned. This bundle has a value of 1. That makes 127. Okay, now, fun times. That's just a 0 for octal. On the other hand, if I want to look at hexadecimal, hexadecimal is very interesting as well. It's based around powers of 16. So if I have 16 to the power of 0, that's 1. 16 to the power of 1 is 16. And then 16 times 16 is 256. And that's about as far as we need to go. So again, we're breaking out 87. And it turns out that there's a nice way to do this as well. I'll just write this out in binary. That was 0, 1, 0. Just like that. Okay. And then I'm going to split this into groups of 4 digits, because 4 digits can represent everything from 0 up to 15, which is a range of 16. I hope that makes sense. So reading this off, I've got 7 and 5. So this would be 57 in hexadecimal. We can confirm that by saying, okay, 5 times 16 is 80, plus 7 times 1 is 87. So, for practical purposes, computers pretty much just use binary, but it's useful for developers to be comfortable with octal and hexadecimal as well, specifically hexadecimal. It's really great for representing bytes. And this is all fine. If this is all we ever needed, yeah, okay, great, we've got our unsigned math. But we do not just do that. Let's say, for instance, I'm looking at negative 87. How can we represent that? Well, there are 3 main systems. We have 1's complement, 2's complement, I hope I'm spelling this right, and excess 128, or something like that. Okay, so the question which all of these are trying to answer is, what is the additive inverse of a number, say 87? So if I have 87, I want some sort of number, which I'll denote negative 87, that has the property that when I add these things together, it gives me 0. Now, this depends on a few things. This depends on how we want to add things together, how we want to define addition in our math system, and it also depends on how we want to define 0. Most of these approaches are very similar, but not all of them. We also have the property that if I apply the additive inverse to an additive inverse, it should cancel out and give me the original. But I'll get that in all of these systems as well. So to start with, 1's complement. So I'll just write this out. This is 87 in binary. Under 1's complement, what I do is I flip all of the bits. So everything is reversed. This has the property that when I go ahead and add the additive inverse to the original, you can see everywhere I'll have just a 0 or a 1. And yeah, this is all 1's. Now, we can define this to be 0 under the 1's complement system. And another way to think about that is, if the definition of a negative number under 1's complement is simply inverting the bits, flipping everything over, then all 1's needs to be 0, because we also have the property that negative 0 has to be equal to 0, right? So if I take this number, flip all the 1's, I would get all 0's, and by that logic, it's linked up. So this is 1's complement. Now, under an 8-bit system, 1's complement will give us, I want to say negative 127 up to 127 in our range. And the reason for that is that there are 2 numbers representing 0. So if you imagine half the numbers are positive, half the numbers are negative, and there are 2 numbers representing 0, yeah, that's our range. Now, on the other hand, we have 2's complement. And the way 2's complement works is the following. First of all, we invert all the bits. And then, finally, we add 1. So if we look up above, imagine that I took all these bits, inverted them, and then added 1. And then I added these together. Now if I add them together without adding 1, I get all 1's. But on the other hand, if I throw in 1 more, we have all 1's plus 1. You'll see what happens. A trick for inverting under 2's complement is I keep writing out the number until I see the first 1. There I have it. From that point on, I invert everything. This might be a bad example for this, because I just see the first 1 straight away, but anyway. There we've got it. And I hope you can see that this is identical to inverting all the bits and then adding 1. Okay, so if I were to add these together, we have 1 plus 1 is 2. So we carry that 1 over, just like that. Now here we have 1 plus 1 is 2, carry again. You can see what I'm doing here. So I added everything up, and I'm carrying over 1. So we could throw this in here. But remember that if we're working in an 8-bit system, then we ignore that final bit, right? We're not going to add 8-bit numbers and get a 9-bit result. That's a little chaotic for our purposes. So this is what's called, actually no, it's not overflow, that's a different thing. I'll talk about this really briefly. You can see here that sort of this leading 1 indicates whether a number is positive or negative. There are cases where we can add positive numbers and suddenly they seem to become negative under a signed system. That's overflow. This is not overflow. This is literally just, that's what we can fit in an 8-bit number, and it's all zeros. Okay, so with 2's complement, we have the property that if I take 0, like let's say we have a bunch of zeros, there's my 0, and then I invert it, so flip all the bits to 1, and then add 1, in this 4-bit example, we get the property that there's one and only one number representing 0, right? I can keep doing that. And so in this case, we can go, I want to say, yeah, negative 127 up to 128. Because again, half the numbers are positive, half the numbers are negative, but we've only got one number representing 0, which gives us a bit of extra headroom. Okay, so that's 2's complement. By the way, little side note, 2's complement was proposed or discovered by John von Neumann when he was working on the Manhattan Project, making the bomb. But some good came out of that because it's a pretty good system. Okay, so XS 128 is a little funky, but basically think of it as our number system has some bias. Bias of 128 to be precise. So the number 0 is actually 128. The number 128 is, well, actually we can't represent that. That'd be too much. The number 127 is the maximum we can represent. That's 255. And the number, I want to say, yeah, negative 128, if we add 128 to that, is 0. So the whole number system is offset by 128. So in our case of 87, 87 plus 128 is 215. So we'd represent the number positive 87 as 215. That is the following, provided I did my math right. Now, the number negative 87 plus 128, it's really 128 minus 87, which is 41, and that would be represented as such. again, provided I did my math right. Now, what this does is, whereas with whereas with 1's complement and 2's complement, it is a little hard to compare numbers. On the other hand, it's very easy to compare numbers under XS128. It's very easy to see which number is bigger than which, because it's a natural ordering. It's still what we're used to. However, it is significantly harder to perform math with them, because with negative numbers, if we add them together, we'll get a number which is bigger and more negative. But in this case, when we add negative numbers together, they start to become positive numbers, which is a little strange. As a matter of fact, have a look at this. If we have 87 plus negative 87, 41 in this case, then this comes out to 2, carry the 1, just keep going here. Something like that. And then what we want to do, because if we carry, there's a 1 carried here, right? So it's 256, I guess, is the answer. But then, well, this was all biased. So what we should do is take away 256 I said, to remove the bias from both of these. That would be all zeros, and then add 128, because what I've done is remove the bias from these two numbers and added in the bias that we're going to use just to represent the number. And here we have 128 as a result, which, as you can see, is 0. So whereas comparing the numbers is very easy, now the math gets a little bit harder. Not super hard, but anyway. So there we have it. That has just been a brief overview of binary systems. Today we looked at 1's complement, just invert all the numbers, 2's complement, invert the numbers and add 1, and XS128, some funky business, to be honest with you. Okay. I hope you enjoyed this, and I will see you again soon. Bye.
Compile and make. I set a point for it to break. The Secret Service calls it treason, but I do this for a reason.